Hello, in this video we're going to look at how we can solve probability problems involving a normal distribution, and particularly when we don't necessarily have nice whole numbers of z-scores that we can use. So let's say we have a study showing that a particular disease lasts for a mean length of 12 days with a standard deviation of 3 days, and that the length of time is normally distributed. So if we want to know the probability that the disease will last between 13 and 15 days, so what's the probability that x is between 13 and 15. Whether we include the 13 and the 15 is kind of irrelevant because this is continuously distributed data. So the odds of something being exactly 13 are very low, since it's probably 12.999 or 12.97 or something like that. So what we do is we use our calculator. We use something called a normal CDF. Now, depending on your calculator, the order in which you put the parameters into the calculator is going to vary. But the things you are going to need to put into the calculator are the mean, which in this case is 12, the standard deviation, which is 3, and you will need a lower and an upper bound. So logically enough, in this instance, that is 13 and 15. Specific instructions for how to use your either Casio or TI calculator to find this can be found in D2L or just honestly by Googling it. So if we are trying to find between 13 and 15 with a mean of 12 and a standard deviation of 3, the probability that our calculator is going to give us is going to be about 0.211 when we round to 3 significant digits. Now, the reason that's very helpful is because the z-scores here aren't whole numbers. So 13 is 1 above the mean, but that's 1/3 of a standard deviation above the mean. And 15 is a whole standard deviation. So if I had looked at this in terms of z-scores, what I would be looking at is a probability that the z-score is between 1/3 of a z-score and 1. And that's simply not something we know from the standard graphs. So we need to use technology or actually a z-score table to find that information. So what do I do in an instance where I don't have one of the bounds? So my calculator requires a mean, a standard deviation, and a lower and an upper bound. But if I don't have, in this case, an upper bound, what can I do? Well, for that, so we want the probability that x is greater than 17. So for that, we're going to use an upper bound that is basically beyond where we would expect anything to ever be found. So I usually go at least 5 standard deviations away from the mean. So you could say, for example, 5 standard deviations would be 15 days. So 12 plus 15 would be 27. Just for safety, you could call it 30. Or you could call it 1,000. Or you could just do 10 to the power of 99 and just make absolutely certain. The differences are going to be so minute that within 3 significant digits, it's not going to matter. If you just put 30 as your upper bound, it would work. But essentially, in this case, I'm going to use my lower bound, is obviously the 17. And then I'm going to use the mean and standard deviation that were here before. I'm going to use 10 to the power of 99, just because that's my standard that I always use. And I get a probability of about 0.478 when I round it, 0.0478. when I round it to 3 significant digits, so about 4.78%. Again, had I used, instead of 10 to the power of 99, had I used just 30, I get essentially the same thing. It's not exactly the same thing. On my calculator, though, it doesn't vary until the 7th decimal place. So I don't particularly care about that level of difference. All right, we can also work backwards on our calculators. So if we know a percentage, we can figure out a value that's associated with it. So let's say we have a particular electronic device with a mean lifespan of 5.3 years and a standard deviation of 0.58. So the manufacturer wants to offer a guarantee, but they don't want to replace more than 5% of the devices. So in other words, if there's a normal distribution of how long these devices last, they're going to replace some bottom end here. And they don't want that to be more than 5%. So we want to know what number goes there. What guarantee should they offer? And this is where we use the inverse normal feature of the calculator. So inverse normal. And again, for that, you're going to need the mean. you're going to need the standard deviation, and you're going to need what it calls an area. So this is always the percentage, or the area, total area under the normal distribution, the normal curve. It all adds up to 1. In calculus, you'll learn what that means, how to find area under a curve using calculus. But the area under this whole curve is 1. And so that area corresponds to 100%. And for inverse normal, we're always going to do area to the left. If your calculator does ask you to give a tail, a lot of them won't, but if you look at your inverse normal, it might ask you for the tail. If it asks for the tail, you're choosing left tail. But the area in this case is going to be 0.05 because that is the percentage that we're looking for. And the mean was 5.3 with a standard deviation of 0.58. So 5.3, 5.58. So when we put that into the inverse normal on their calculator, we get approximately 4.35. Now, you're not going to offer a guarantee of 4.35 years. So you're probably, for example, going to say 4 years. And if I choose 4 years, then that's going to be more than 5%. Because if this right here is 4.35, then 4 is going to be somewhere over, that's going to be good. 4 is going to be over here. So that's going to be less than 5% that I'm going to have to replace. So about 4 years would be a reasonable warranty on this item. We can also use the calculator to determine just generic ones that aren't necessarily in a context. So given some random variable x that is normally distributed with a mean of 36 and a standard deviation of 3, if we want the probability that x is less than 32, so 32 is on the left-hand side of the mean, we want this probability here. It's going to be less than 50%. We're going to use a normal CDF, and here we don't have a lower bound. So again, you can use a normal bound that's, let's say, like if I said 0, 0 is 12 standard deviations below the mean. So that's definitely going to be enough. Or you could say negative a million, whatever you want as a lower bound, but it has to be far enough away from the mean that it's not going to be highly probable anymore. So I'm going to use a lower bound just of 0. My upper bound is 32. The mean is 36 and the standard deviation is 3. So again, depending on your calculator, you'll enter those in a slightly different order, but you're always using normal CDF. And what we get here is about 0.0912. I'm going to give it as a percentage, 9.12% when I put it to 3 significant digits. If I want the probability that something is going to be greater than 40, so 40 is on the right-hand side of the mean, and I want the probability of it being greater, well, hold on here. If I look at that, 32 was 4 units below the mean, and 40 is 4 units above the mean. So this should be symmetrical. I should get 9.12% again. And in fact, if I do this using a lower bound of 40 and an upper bound of, say, 1,000, just to be absolutely certain, then I get 9.12%. If I want the probability of something being between, that's a little bit easier, but 18 to 25 are both on the left-hand side of the mean. So again, I'm expecting something not super big as a percentage. So the normal CDF with a minimum of 18 and an upper bound of 25 is going to give me a probability. So if I put it in a percentage, because it's a very, very tiny number, I get 0.0123%. So I've already multiplied this by 100, and it's still that little, which again is logical because the upper bound of this 25 is already more than 3 standard deviations below this mean. So in fact, it should be incredibly rare.